Hi guys, let's continue our look at reactions of aromatics, focusing on benzene here. In the previous video we looked at halogenation, nitration, sulfonation, and this was our outline here that you can use to see the various topics we covered. And next on the list here is the Friedel-Crafts alkylation. Okay, and that would be putting on carbon groups, either an R group, alkyl group, or we'll see later an acyl group. But before we get to those reactions, let's take a detour a little bit and look at substituent effects in the EAS reaction. We mentioned this at the end of the last video. If you have a benzene compound and there's already a substituent there, where will the next substituent be introduced relative to the current substituent? Now on the warm-up page, we had a benzene ring that had 4 substituents. And really we're asking, where's this chlorine going to end up? Okay. Now you note, doing chlorine, we could use a Lewis acid such as FeCl3. All right. What would be an appropriate catalyst for this chlorination reaction? Yeah, we looked at that. But where would the chlorine be introduced? And to answer this, we need to understand the different substituent effects. What effect does each substituent play on directing the new group? Okay, that's some of the terminology. But we'll also look at, and the first thing we'll look at, Roman numeral 1, what I was referring to is actually directing effects. That's actually going to be Roman numeral 2. Where's the new group going to go compared to the existing group in the starting material? But I see we're going to start with Roman numeral 1, activation, deactivation of the ring towards the reaction. That is, if we have an existing group, does that group make the benzene ring more reactive or less reactive? Okay. Now, here we go. If you have an electron donating group on the ring, now I'm a net donator, because sometimes groups can do both. They can both withdraw and donate. But if the net effect is to be a donating group, okay, electron donator, by either induction or resonance, and we'll look at examples, that compound is going to be more reactive than benzene. More reactive than if that group was not there. Now if the group is a net electron withdrawing group, that's going to make that compound less reactive than benzene. Now you got to keep in mind that in an EAS mechanism, the benzene ring is acting as a nucleophile. How do you make nucleophiles more reactive? You increase their electron density. If this is a donating group, we're going to increase the electron density of the ring, and that's going to make it a stronger nucleophile. It would then be more reactive than benzene. If we remove electron density from the ring, that's going to make it less reactive as a nucleophile, and thus less reactive than benzene, or if the group was not there. Now we can explain this also by looking at reaction coordinate diagrams. In the middle we see benzene. If we do an EAS mechanism, we have an activation energy leading to our sigma complex intermediate. Right? Sigma complex. Resonance stabilized. If we have a donating group, a net donator on the ring, pumping electron density into the ring, that will stabilize this carbocation. Now we'll look at specifics of how this stabilizes it, a lot of times by resonance, sometimes by induction. But in general, donation will stabilize the positive charge, and thus this intermediate will be lower in energy compared to if that donating group was not there. If the intermediate is lower in energy, typically the transition state leading to it will be lower in energy. And this reaction will occur faster than if the group was not there. Now just the opposite, if we had an electron withdrawing group on the ring, net, pulling electrons away, well, that's not going to stabilize a positively charged intermediate. That will destabilize it, make it less stable than if the group was not there. And a less stable intermediate will have a higher transition state energy leading to it. And that will be a more difficult reaction compared to the reaction if the withdrawing group was not there. All right. Now, that should be pretty straightforward. What we need to look at in detail is what groups are net donators, what groups are net withdrawers, and then how do each of those groups act? Do they act by resonance or do they act by induction? All right, we'll look at these groups. We'll also group them into, I believe, 4 different groups, Roman numeral 1 through 4. Different types of substituents that we will see on the benzene ring. Or for that matter, any aromatic. But benzene, of course, is the most common. Okay, group 1. Now this is my grouping. All right, I'll show you a table from a textbook. The groupings may be a little bit different. Okay, over here, they actually just show, well, a little bit different. There's 4 groups there. We'll get to that. My group 1 I call strong activators / donators. All right. Now if we go back up here, if the group makes the molecule more reactive than benzene, it's going to be an activator, we call it. If the group makes the ring less reactive than just simple benzene, it would be called a deactivator. Now group 1 are going to be strong activators. We can also call them strong donators because, of course, an activator is a donating group, right? But these I'm calling strong. When we get over to group 2, these will also be activators, but these are going to be considered weak, all right, or not as strong. The strong activators are atoms with a lone pair other than halogen, okay? Not halogen. And this will include, most commonly, oxygen and nitrogen. But it could include other atoms. For example, a sulfur. Any atom with a lone pair other than halogen. All right. Now, why are these strong activators / donators? Well, these atoms typically are more electronegative than carbon. Hold on. If they're more electronegative than carbon, that means they withdraw by induction. Right? Because if you have a CO bond, if the carbon is part of the ring, okay, if that's the benzene ring, doesn't the oxygen withdraw inductively? Yes. But we said they were donators. That's because even though these withdraw inductively because they are more electronegative than carbon, okay, their donation by resonance is very strong and is thus the predominant or overriding effect. Okay? So this is a case where the oxygen with a lone pair is going to have two sort of ways it donates or withdraws inductively. It would, or two electronic effects. It withdraws inductively due to being more electronegative, but it can donate by resonance. And it turns out that the donation by resonance is the major effect, and thus it is a net donator. Now we can see there's two different ways to show the resonance donation. One is we can show it as from the starting material. The other way is to show it at the point of the carbocation sigma complex. Here I'm going to show it from the starting material, and we can just do resonance structures, and these electrons here and these electrons out. Of course, this compound is called, what's the name of this compound? Anisole, right? And we see by resonance we're putting electron density into the ring or onto one of the ring atoms. But we can keep going. These electrons can move in here. These electrons, pi electrons, move out. We can keep going again. Double-headed resonance arrow, of course. These electrons can move in here. These electrons can move out. Of course, either one of these lines I can consider the pi bond. Doesn't have to be the inside one. Whatever's convenient for your drawing here. So this arrow puts pi bond here. Nothing changed here. Nothing changed here. But now pi electrons move out onto this carbon as a lone pair. That's minus. And there we go. Now if we take these electrons and move them here and move this bonding pair back onto oxygen, we would get back the original. Except the pi bonds in the benzene ring would be a little bit different, and that's just resonance of the benzene ring. So these resonance structures show the electron donation from the methoxy group by resonance into the benzene ring. And it's important to point out here that the negative charge falls on the ortho, para, and ortho carbons compared to the placement of the methoxy group. And it's the ortho and para positions in the ring that have increased electron density due to the methoxy group being conjugated with the benzene ring. Okay. We're sort of setting the stage here. We'll continue to develop this. Need to be able to draw resonance structures using existing groups on the ring. Basically, in summary, group 1 are atoms with a lone pair, but not halogen. We will sum this up once we go through the different groups. Group 2. Now, group 2 is also an activating group, but it's a weak activator. It's not as strong as group 1. There's two types of subgroups here: conjugated pi bonds and alkyl groups. This is an example of a conjugated pi bond with this alkene conjugated with the benzene ring. We can also show resonance structures. Here we do not have a lone pair, but we can use the alkene like a windshield wiper. Electrons move over here, pi electrons move out. We can get this resonance structure, and we see that the ortho position has increased electron density due to the group. Okay. Now this is resonance donation, and you can keep going here. At this point we can just move electrons around the ring very much like we did here. Here though, we started with a lone pair on the existing group. Here the existing group doesn't have a lone pair, but instead has a pi bond. It's particularly an alkene, because you wouldn't want this to be a carbonyl. And the resonance here, donation of the pi bond, is weaker than the donation by a lone pair. Lone pairs donate stronger by resonance because they're not bonding. Also, when we do this, we leave a carbocation with no octet, and so this is not a great resonance structure. Not as good. It's still reasonable, but this is a weaker effect. All right. Now we can also consider a sigma complex. A sigma complex may look something like this. Okay, and if the group wasn't there, we can do resonance around the ring. All right, and we did that early on. Right here, resonance around the ring. And here the electrophile was added. All right. Over here, the electrophile looks like it may have been bromine. All right. And the carbocation fell next door, ortho. The carbocation is next door to the electrophile, the bromine, ortho. But from this point, in addition to moving this charge around the ring by resonance, we can also do resonance from this alkene group. Okay? And so we have an additional resonance structure from the alkene group, and that's going to stabilize the sigma complex. But again, this is not lone pair donation. And the pi bond donation is weaker than lone pair donation. Now the second subgroup here is your alkyl groups, like a methyl. This compound being called toluene, yeah? Donates by induction. Now here we can't show any resonance structures, because you don't show resonance structures when you talk about induction. This is sigma bonds. But if we consider a sigma complex, okay, just like above, and we show resonance structures, we can do these down like this, And of course you can windshield wiper these up like this. Here are our 3 resonance structures, the same as we drew over here. Okay. How will this methyl group affect this carbocation that we see here? Well, right here we can talk about the methyl group donating to stabilize the carbocation. All right. Is this carbocation more stable with the methyl? Yes. If the methyl wasn't there, you would not have this inductive donation, the inductive stabilization. With it there, the argument is inductive donation. Alkyl groups donate by induction. Now this is weaker than resonance. Particularly it's weaker than lone pair resonance. Okay, over here this was going to be lone pair resonance. It's comparable to pi bond resonance. That's why both of these are considered weak activators, kind of grouped together. Okay, so alkyl groups fall here. Now benzene would fall here. Now group 3 are going to be less reactive than benzene, while group 1 and 2 were more reactive. And group 3 are weak deactivators, weak withdrawers. And this is where the halogens fall. It's the most common example of group 3. Now the halogen, like a chlorine, does have a lone pair. Now in terms of induction, they withdraw inductively. Because they have a lone pair, they donate by resonance. But with the halogen, the withdrawing is the major effect. The inductive withdrawing is the major effect. But with other atoms, such as oxygen, nitrogen, sulfur, the donation by resonance is the predominant effect. All right. And since this is the predominant effect, they are net withdrawers and thus net deactivators. Now it turns out they're weak compared to group 4, which we'll see next. All right. So chlorobenzene is less reactive towards an EAS reaction than benzene. And benzene is less reactive than toluene. And toluene is less reactive than anisole. Of course, there's other compounds that we can discuss. These are the examples shown here to illustrate each group. Group 4, these are your strong deactivators and thus strong withdrawers. These are going to be electron-poor atoms. Okay? And we're talking about an atom bonded to the benzene ring. The atom bonded to the benzene ring is electron poor and it will have no lone pair. Because if it had a lone pair, it would either be a halogen or it would be one of these over in group 1. So no lone pair. And as they have no lone pair, they can't donate by resonance. They only withdraw inductively. And thus the withdrawal is their main effect, and it's thus a strong effect. Now they can also actually withdraw by resonance. And that's not really discussed here. But they cannot donate in any way, and thus they are considered strong withdrawers and thus strong deactivators. Examples here include your nitro group. Okay? If this was bonded to a ring, this nitrogen having a positive charge would be electron poor, and it also does not have a lone pair. Sulfones or sulfonic acids or sulfonamides also fall here because the sulfur is electron poor, having these two oxygens bonded to it. It also has no lone pair. A carbonyl group, which is very common. The carbon is electron poor because of the dipole here. Carbon does not have a lone pair. The cyano group or nitrile. The carbon is electron poor because of the dipole, and the carbon does not have a lone pair. So these are considered strong withdrawers and thus strong deactivators. Now review. You can list these four compounds here. Phenol is more reactive than toluene. See, that's a group 1, right? That's a group 2. Bromobenzene, the bromine, would be group 3. The methyl ester would be group 4 because that's a carbonyl carbon bonded to the ring. Group 1, 2, 3, and 4. See, phenol is much more reactive than like bromobenzene or this compound here, which is the methyl ester of benzoic acid. Now you got to be careful. You might be quick to say that an ester is a net withdrawing group, a deactivator, a strong deactivator. But this here is also an ester group. It's just sort of switched, and the oxygen is on this side bonded to the ring. Now here you have an atom with a lone pair bonded to the ring, and it's not halogen. So this is actually group 1. A question could become, which is more reactive or activated towards an EAS? Phenol or this compound here, which really doesn't have a common name. We'll just call it this compound here. Okay? Well, the answer is phenol, because while this oxygen can donate to the ring, it's also donating the other way. Okay? We can draw resonance into the carbonyl. And if it's donating the other way, it's going to be less likely to donate fully into the ring. So while it is group 1, you would predict it not to be as reactive towards an EAS as phenol would be. Here's some actual numbers. If you look at anisole towards an EAS, this is towards nitration, which is an EAS mechanism. Compared to benzene, it's 10,000 times more reactive than benzene towards nitration. Toluene is only 25 times more reactive. All right, of course, benzene would sit here. So weak activator, a strong activator. Then a nitro group is a strong deactivator, group 4, and it should be less reactive towards nitration than benzene. And it's 100,000 times slower to nitrate than benzene. And when we're talking about nitrating, we're talking about putting a second nitro group on nitrobenzene to make dinitrobenzene. Once you put one group on, the ring becomes deactivated. and putting the second nitro group on is 100,000 times slower than putting the first one on, starting with benzene. Now, what if you have multiple groups? Well, it turns out the effects are additive. Okay? You can just sort of sum them up. All right? Consider this for homework. Which one of these is most reactive towards an EAS? Why don't you rank these in order from most reactive to least reactive? Now this is a table that sort of shows what we're talking about. This came out of a textbook, presented a little bit differently. When I first looked at this, I was looking at my handwriting. They actually have 6 groups. 1, 2, 3, 4, 5, 6. Because instead of having 2 and 2, they distinguish between strongly activating, moderately activating, and weakly activating. Now if you note, here's the oxygen bonded to the carbonyl. And previously I compared that to like the OH. Alright? That's what we did right here. I called it group 1. But I did say that these two group 1 substituents are different, because this one, the electrons are conjugated with the carbonyl, and so you can thus show resonance structures into the carbonyl, and you can delocalize the lone pair onto this oxygen, pulling electrons away from the ring. So it doesn't donate as strongly to the ring as the OH that doesn't have that group. And this table sort of distinguishes that, having carbonyls on the nitrogen or oxygen. But then they show the weak activating, that was your alkyl group or R groups. Also your pi bond. I showed an alkene. Could be another aromatic. Okay? For example, if you had one aromatic and then you had another one, if you were focusing on this ring to do an EAS, you could say, well, what's the effect of the other? Well, it's really just a pi bond here. The same as if that was, you know, something like this. Both of these you have carbon-carbon pi bonds that you can use to come in here and do resonance to stabilize a carbocation. And you might also think about fluorine, the ring system. And if you're doing a reaction with one ring, how does the other ring influence that? Because this is a long bond here as we've drawn it, but basically this ring is directly bonded to the other ring through here. Now of course here you have an sp3 carbon, but up here they're directly bonded just like they're directly bonded here. Standard of comparison is H. This is where it would just be benzene, yeah? Then your halogens are your group 3. And then all of these I would consider group 4. They just distinguish between moderate and strong deactivating. Now the directing effects are also shown here. We will talk about the directing effects in the next video. Important note. Okay? An NH2 group, or any amine, is strongly activating. But in the presence of acid, either proton acid or Lewis acid, these basic amino groups become protonated or somehow complex with the Lewis acid. And if that happens, the nitrogen becomes positively charged. And at that point, it no longer has a lone pair and it's electron poor. And then it becomes a group 4 atom, which is then a strong deactivator. So an amino group under acidic conditions is actually converted to a strong deactivating group. So your pH or your reaction conditions could be important. You don't want to be modifying your group by maybe pH chemistry or acid-base chemistry. All right, something to think about there. Okay. So ultimately, you see a compound, and by the way, we have our nomenclature over here in the aromaticity warm-up, and we can ask questions, okay? Let's see. Let's compare toluene to acetophenone. Which one will brominate faster if we react it with bromine and something like FeBr3? All right. So that's what we're talking about. We have to understand the activating or deactivating effects of common groups to be able to predict that answer. Or we could ask a comparison to benzene. Which will nitrate faster, benzene or benzoic acid? So, activation, deactivation effects. In the next video, we will talk about directing effects. If you have a group, where will a new group end up? Will the new group end up ortho to the existing group, meta, or para? So this is directing effects. All right. Of course, you can also be reading in your textbook. All right. And that's the remainder of this handout. Both of these together are considered, okay, substituent effects for our EAS reaction mechanism. Okay, guys.